All right, in this video, we are going to move into section 3.4, our first of two sections on the idea of optimization. In this section, we're going to focus on optimization in the way of finding absolute, maximum, and minimum values. So if you remember from sections 3.1 and 3.2 video, we talked about how to find relative extrema, so like relative max and mins. Today, we're going to do one extra little step, and it's actually an easier step, to be able to find what absolute maximum and minimum values are. So let's talk about this idea. So let's suppose you have f of x, which is a function defined over a domain I. Then what we can say is that f of c, and remember c is your critical value we've talked about, f of c will be an absolute minimum if f of c is always less than or equal to f of x for all x and I. AKA, that's the mathematical definition. In layman's terms, it will be an absolute min if it is the lowest point on your graph, which makes sense. An absolute min has to be the lowest point. Versus you can read through the definition for absolute max. It's very similar mathematically, but if something is an absolute max, that means it has to be the highest point on your graph. Now, if you look down here at this picture that I have, you can look at all the values that are listed. You'll see some relative extrema. You'll see some absolute extrema. Let's focus on the absolute part. If you look here at C1, you can tell without a doubt that this is the lowest point on the graph. And even though it does fall under the definition of relative min, because if you look at that point, you're going from increasing to decreasing, and we've always called that a relative min. But since it is the lowest point on the graph, it's also called an absolute minimum. Now, what you'll notice is a little bit different here is that your absolute max, it actually occurs at the very end of this picture, because unlike relative max and min, absolute max and mins don't have to follow the increasing and decreasing rules. It only has to exist at the highest points. Now that can get a little tricky, especially when you don't have a graph, because what if it doesn't go from increasing to decreasing like this one? How would you go about testing for that point? That brings up one last little point that I kind of covered up down here at the bottom. Notice that an absolute max or min can occur at the end point of an interval. So we're going to have to come up with a way that we can always double check to make sure that our absolute max and min doesn't occur at one of your endpoints. So there is a way and there is an idea behind how we do this, and it requires a little bit of note talking here, or note taking by y'all, a little bit of talking by me. So let's kind of go through this. So first off, the first theorem has nothing to do with how you'll answer the question, but it does guarantee us something that helps us out. It's called the extreme value theorem, and it says the following. If you have a continuous function f defined over a closed interval a to b, and this is key, if you have a closed interval defined, then you must, and this is the key, you must have not only an absolute maximum value, but you have to also have an absolute minimum value. You have to have both. That only is true if you have a closed interval. We'll see an example a little bit later where you don't have a closed interval, and we'll talk about what you'll do with that later. Now, how do we actually go about solving this problem? So there's a theorem called the maximum minimum principle, and this is the technique we will use to find absolute max and mins. So part A, find your derivative. Just like you normally would in a graphing problem, find f prime. Find all of your critical values. The only difference here is that you need to make sure that your critical values only occur in the interval a to b. Anything that falls outside that interval is not useful for us. Remember that critical numbers come from taking the derivative and either setting it equal to 0, or if you have a fraction, figuring out where it does not exist. You need to list the values from step B And you need to also locate the endpoints of the interval. Because as we talked about, an absolute max and min can occur at an endpoint. And then here's where kind of the tedious part goes. You need to take every value from step C. So that's all the critical values and your endpoints, and you have to evaluate the original function at all those points. So it's a lot of number crunching in your calculator, all right? So you'll get your calculator out, and you're going to plug all these numbers into the original function. Whichever one of these numbers gives you the largest value is your absolute maximum, versus the smallest value you get will be your absolute minimum. And when we get to our first problem and we answer it, I'm going to talk through a little bit about how we'll answer these questions, because it will be a little bit different when you get to your homework and quiz. But this is the steps we're going to go through. That's the bulk of what this section is. How to find absolute max and mins. All right, before we get to one where you have to do the calculus part, let's make sure we can read this from a graph to understand what you're looking for. So number one, according to the U.S. Department of Energy, a vehicle's fuel economy in miles per gallon decreases significantly at speeds over 60 miles an hour. I want you to do the following three things. So we're going to do them all together. Part A, estimate the speed at which the absolute maximum fuel economy is obtained. So if you look up here and you're looking for the maximum fuel economy, you're trying to figure out what's the highest point on this graph. It looks like ever so slightly that your maximum is going to occur at this point right here. And if you look straight down, that is occurring at 55 miles per hour. So if you're going 55 miles per hour, you will maximize your fuel economy based on this data. Part B, estimate the speed at which the absolute minimum fuel economy is obtained. So you're looking at your graph and you're trying to find the lowest point. Well, as we've talked about, your lowest point can occur at an endpoint, and it does here. It occurs at that very first dot. That is when you're traveling 5 miles per hour. So if you drive 5 miles per hour, you're actually going to get the worst fuel economy out there. And then finally, part C, being able to go the other direction is also helpful. So how about this? Can you tell me what is the fuel economy obtained at 70 miles per hour? So if I go over here to 70, which is this point right here, and go up, it looks like you're crossing at that point right there. If you look to the left, it looks like you're going to be getting 25 miles per gallon when you are driving 70 miles per hour. That is not a maximum or a minimum, but knowing the X value and finding the Y is going to be the big thing in the problems we're about to work. Very good. All right, so now let's work on that maximum modulus principle. So I've got a bunch of these to work, and that's pretty much going to be the bulk of the rest of this video. So number two, and these instructions are the same for the next 4 or 5 problems, so I'm not going to repeat them every time. It says find the absolute max and minimum values of each function over the indicated interval and indicate the X values at which they occur. So we're going to begin with f of x equals 2x plus 4 on the interval -1 to 1. So going through my steps I showed you earlier. Step number 1, you need to find the derivative of your function. The derivative of 2x plus 4 is 2. Now, step 2 says actually find the critical values. The problem is, though, is that if you set this derivative equal to 0, that's impossible. So actually, there are no critical numbers in this problem. That doesn't mean there's not an answer. So please don't put no answer. What you have to do is we are going to set up, and this is how I do it, and I do this different than a lot of other people. Part 3 says collect all the numbers you're going to test. Now, while this is going to seem very childish, it keeps everything very organized. I'm going to make an X and Y table on every problem we do this on. First thing I would do is I would list my critical numbers, but I don't have any. But remember, you have to also list your endpoints. So even though I don't have any critical numbers, my endpoints still have to be tested. All the numbers that you list out, you are now going to substitute those into the original function. This is where you can use your calculator a bunch. If you plug -1 into the original function, you should get a value of 2. And if you plug +1 into the original function, you should get an answer of 6. Now, on your homework, you're going to have to be very careful about how they answer these. Most of the problems are going to look like this. They're going to ask you for the absolute minimum value, and then they're also going to ask you for the absolute minimum location. So these are two different answers you will have to give. Your absolute minimum value will be the smallest y value that you find over here. That's going to be at 2. So 2 would be your absolute min value. The location is the x value that you find, which is -1. And I know that looks a little weird of how they want you to answer, but you're having to keep track of what the value is, and that's the y value, and location is x. You can do the exact same thing for the absolute maximum value and the absolute maximum location. Well, the largest y value that we found was 6, so that would be your absolute maximum value, and it located at x equals 1. And that's how you'll answer these questions when you get to your assignments. So that's how I'm going to answer every question we do today of this type, so be prepared for this same little grid every time. So I made up a variety of different questions we can answer here, so let's work through a bunch of these. So number 3, same instructions. I want you to work with f of x equals x squared minus 6x minus 3 on the interval -1 to 5. So first thing I'm going to do is I need to find the derivative of my function. So that's f prime of x. That will be 2x minus 6. And I'm going to set that equal to 0 to find the critical values. If I add the 6 over to the right, that is 2x equals 6. And if I divide both sides by 2, that is x equals 3. I'm going to make my t-chart like I did just a minute ago. This time I'm going to take my critical value, which is 3, and I'm going to list that number first. And then I'm also going to list both of my endpoints, because that's part of the process. Getting my calculator out, I'm going to plug all 3 of these numbers back into the original function. So you can pause and follow along if you'd like, and I'm going to kind of knock this out really quick. So when I plug 3 in, I got an answer of -12. When I plug -1 in, I got an answer of 4. And when I plugged 5 in, I got an answer of -8. So first thing I'll do is locate my biggest and smallest numbers. Obviously, the biggest number is going to be this 4, because that's the only positive number we got. And -12 is your smallest number. So as far as those blanks go, your absolute maximum value will be equal to 5, and the location of that is equal to -1, because that's the x value of that number. If I do the absolute minimum value, the lowest number I found was -12, and it occurred at a location of 3, because that's the x value. Answers for this problem. You have an absolute maximum and an absolute minimum. All right, let's do another one. So this time f of x is equal to x cubed plus 1/2 x squared minus 2x plus 4 on the interval -2 to 0. So I'm going to find my critical value first. So I need to find f prime of x, which will be 3x squared. Let's see, that's going to be plus x when it's done, and then minus 2. I'm going to set that equal to 0 and factor. So let's see, I've got to factor this quadratic. That would be 3x and x. Let's see, that's going to be 1 and 2. That's got to be plus and then minus. So there's my factored form, 3x minus 2 and x plus 1. I'm going to set both of these equal to 0. The first one, if you add 2 to both sides, you get 3x equals 2. And if you divide by 3, you get x equals 2/3. The second one, if you subtract 1, you get x equals -1. And for the first time, there's an issue we have to be aware of. And this doesn't happen very often, but it happens on this one. Remember, the original interval is only between -2 and 0. If you happen to get a critical value that doesn't fall between those two numbers, you have to exclude it. Positive 2/3 does not fall between -2 and 0. So actually, we get to exclude the 2/3 because it doesn't work for this problem. -1 does fall in that interval, so we can keep that one there. So when I make my t-chart here, the only critical value that I'm going to include is -1, and then I'm also going to include the two endpoints, which are -2 and 0. Once again, you are plugging those three numbers into the original problem. If you want to pause the video and try this yourself, you can, but I'm going to continue on and type all this in. So give me 1 second if you're just waiting. So when I plug -1 in, remember fraction form, I got 11/2. Right? When I plug -2 in, I got +2. And when I plug 0 in, I got 4. So looking at those three y values right here, the smallest number is going to end up being this 2. So that's going to be my minimum. And then just double checking, 11/2 is about 5.5, and 5.5 is bigger than 4. So this is going to be your maximum. So to answer my questions, if you have your absolute maximum value, that's going to be 11/2, and the location of that one occurred at -1. Your absolute minimum value, in this case, is 2, and it occurs at a location of -2. And there are the values that you need for your absolute max and min. Let's keep going. Like I said, I'm trying to throw out every kind that you might see. So number 5, what if f of x is equal to x to the 4th minus 2x cubed on the interval -2 to 1? So once again, I need to find my critical values for this problem. So I'm going to find f prime of x, which is equal to 4x cubed minus 6x squared, and I'm going to set that equal to 0. Let's see, this one's going to be factored by GCF, so both of those terms share a 2x squared in common, and you should have a 2x minus 3 left over. Set both of those factors equal to 0. The first one, if you divide by 2, that is still x squared equals 0. And if you take the square root of both sides, it's still going to be 0. The second one, if you add 3 to both sides, you get 2x equals 3. And if you divide both sides by 2, you get x equals 3/2. And you run into the same issue that we ran in on the last one. The interval that we're working on is between -2 and 1. One of the numbers we just found does not fall between there. 3 over 2 is actually equal to 1.5. So this fraction is too large for our interval, so we're going to exclude it. 0 is in the interval, so we can keep that one there. I'm going to make my t-chart. The only critical value I'm checking is 0, and then I'm going to check my two endpoints, which are -2 and 1. I'm going to plug these three values back into the original function. So if you plug 0 in, that's a pretty easy one to do. You're just going to get 0. If you plug -2 in, let me make sure I get this right, you get 32. And if you plug 1 in, you'll get -1. Looking at those values, it looks like the largest value is the 32, which will be your maximum, and -1 is your smallest, so that will be your minimum. So when I answer my same questions again, you will have an absolute maximum value equal to 32 with a location equal to -2. And then you will have an absolute minimum value equal to -1 at a location equal to +1. And there is your absolute max and min. All right, now we get to an issue where what happens if you don't have a closed interval? So we don't see this a lot, but here's one example to show you how it works. So same instructions. This time we're going to do f of x equals x squared plus 432 divided by x. Notice though that the interval is from 0 to infinity. This is not a closed interval. So what that means is that you are not guaranteed to have an absolute max and min. What you will have to do is find the critical values of this and figure out which one it is if you have any of them. So first thing I'm going to do is find the critical values of this function. Before I find the derivative of f of x, as we've done numerous times in these videos, I'm going to rewrite this second term as plus 432 x to the -1. When I find f prime of x, that's going to be 2x minus 432 x to the -2. I'm going to rewrite this as 2x minus 432 divided by x squared, and we're going to set this equal to 0 to solve for your critical values. There's a couple ways you can solve this. I think the easiest thing to do here is just to multiply everything by x squared, because that will get rid of the extra fraction that you don't need. So this would actually end up equaling 2x cubed minus 432, because the x squareds would cancel, and then the 0 on the right actually remains unchanged. All right, set this equal to 0. If I move the 432 over, that is 4x cubed equals 432. If I divide both sides by 2, that is x cubed equals 216. And then if you take the cube root of 216, so cube root, we can say that x is equal to 6. Now, you can't throw any critical numbers out unless it was negative, because any number between 0 and infinity is fine. The thing is that I don't know whether this is an absolute max or min, so I'm going to have to resort back to the line test that we did back in section 3.1. So I'm going to plot the 6 right in the middle. I'm going to pick some test values, so let's say 1 and 7, and you're going to plug them into, I probably should have done this in red, so let me cover this up in red so it's a different color. 1 and 7, we're going to plug these into this first derivative that we found up here. If you plug 1 into this, you should get a negative number, which means you are decreasing. If you plug in a 7, you should get a positive answer, which means you're increasing. So as you can tell, this graph goes from decreasing to increasing. So what that allows us to now say is that this 6 has to be a minimum. And not only is it a minimum in this problem, based on the instructions, it's an absolute minimum. So you would have an absolute minimum value of, whoops, I haven't found that yet. I know that my location is going to equal 6 because that's the x value. Remember, to get the value, I need to plug this 6 back into the original problem. So if I do that, I should get a y value of 108. So I have an absolute min value of 108 at a location of 6. And if it does ask for the absolute max on this problem, there's not one because there's just not one. It's not a closed interval, so you're not guaranteed to have both. You only have one extrema, so it has to be an absolute min. All right, so to end this video, we are going to do a word problem like you've probably gotten used to by now. So let's knock out this problem to end this video. It says an employee's monthly productivity M in number of units produced is found to be a function of T, which represents the number of years of employment. For a certain product, a productivity function is given by M of T equals negative 2T squared plus 100T plus 180 on the interval 0 to 40. Find the maximum productivity in the year in which it is achieved. So when it says find the maximum productivity, you are looking for the absolute maximum in this problem. They gave us a function. They gave us an interval. This 0 to 40 can be written this way as well. So we can work this just like the first 4 or 5 problems we did in this section. So step number 1 is I need to find my critical values. So I need to find m prime of t. So take the derivative of your function. That would be negative 4t plus 100. And I'm going to set that equal to 0. Subtract the 100 over. So negative 4t equals negative 100. And then dividing both sides by 4 gives me t equals 25. 25 falls in my interval, so it's okay. I'm going to make a t-chart. Now, normally I would call this x and y, but since my variable is t, we'll call this t and y. My only critical value is 25, and then I have to check my endpoints, which are 0 and 40. And you're going to plug these 3 numbers back into the original function. So let's see, if I start by plugging 25 in, I get a value of 1,430. If I plug 0 in, I get a value of 180. And if I plug 40 in, I get 980. So it says, find the absolute maximum productivity. Well, based on this, your maximum productivity is going to equal the largest number you found, which is actually equal to 1,430. And the year in which it occurs is in the t value. So that would be the 25th year. So based on this data and based on this function, an employee is the most productive in their 25th year of employment, starting from their 0th year, which is when they're hired, up to their 40th year when they retire. That ends the video for section 3.4. That is, how do you find absolute max and mins, which is a form of optimization. In the next video, we're going to do more optimization, but more in the word problem sense with multiple functions. So we'll see that in the next video.